Okay, let me just. Well, hello, good morning. Uh, so my name is Rodrigo França. I'm from Brazil, from Instituto Maior de Tecnologia. Uh, and I want to present a case study that we are creating, right, from the uh, virtualization of a space instrument for software development purpose. So just first, just a bit of context before I actually begin. Uh, this idea came from we work on the Plato project with a partnership with some laboratories in ISA, especially Lesia at France and DLR at Germany. And we created a hard simulator for them that was able to talk in space-wide interface and simulate some of the satellite cameras for their software development testing. And well, it worked fortunately. And then they asked they we asked for if they had new opportunity, and gave us a challenge that was we want to we are developing the Vinspec M instrument software, and we want to start doing it without the needs of a hardware and be able to do it on I don't know virtualized setup. So we try to use that expertise to begin developing this. So I'll present a bit more the idea and what exactly do we intend to do with it, and what we see as opportunities to improve what they have currently. Okay. Well, just the outline, but again, the contest is space hardware is hard to make. It's complicated. It's take a long time. So the idea is to have a virtualized hardware that follows the specs, the original specs, but you can play with it more and try different things and try even destructive things that you don't want to try on a real hardware. Uh, this would allow you to have more flexibility, less cost, more risk mitigation, and also, when you have a virtualized system, I will show it with more details. It's all content using containers. You can put it on CI/CD integration servers and do automated testing and things that's hard to do with real hardware, right? So the objective in the end of the day is to reduce the hardware dependency, a dependency in the stage of development, and also a very interesting part of the hardware, the simulator that we developed, the Simulcan, is the ability to inject errors. So we could inject failures at any time the user wanted on the, for example, the spacewire protocol or AirMap protocol or image failures. We could simulate all kind of bad behavior that could happen on a real mission, uh, so their software will be ready for that. So what it does when the camera suddenly stops sending images during a cycle? Well, it need to be able to comply with that. So we are able to inject all this kind of failures, all programmatically on the hardware. So the idea is to bring this to a virtualized instrument. So during the test, during the validation, it should all be possible to send comments to inject failures, for example, corrupt a part of the memory, or maybe change a part of the payload, anything that could happen on a real space flight, but everything virtualized. And the idea is also to have the potential future integration of real hardware. So we are actually, I will show a setup, but we are actually testing how to communicate the virtualized system with real systems. Okay. So just a bit more context about the mission itself. The VanSpec mission is the Veritas mission is a mission to study Venus. It's led by NASA, but ESA is doing some of the instruments, and DLR is working on a near-infrared spectrometer uh, to measure some of the characteristics of the planets. Right? Is one of the instruments that will be there. It should gather mineralogical data by analyzing infrared windows. So, and the hard part of the software development, I think it's common to all aerospace area, is the extreme operating environment. So, especially Venus is a very bad atmosphere and very bad conditions, but in space overall, you had the radiation, you have all kinds of issues. It needs high specialized hardware, so it will be a Leon 3 based processor, right? And it needs to be robust, verifiable software to ensure the mission success. I believe they don't even need to say this here, but no. Uh, and this is just what's supposed to be the vein or the vein spec ham. It has all the near infrared spectrography part and electronic controller. That is what we are trying to emulate. And in this process, a important question was which tools we use for it. And since we are a university at Brazil, we didn't want to use very expensive closed tools, so we chose to use Kimu, the that's widely used to simulate computer architectures, right? Uh, Also, not only it's open source and completely free, but it also has the advantage of already having a Leon tree simulation embedded in it. So it can already simulate the Leon tree, but cannot simulate the instrument itself, for example. So that's the modification we are doing, right? And also, we want to use Docker for containerize everything. So we have a consistent package that we can deliver to the clients and can deliver to the laboratories and can test in the same setup in our system and avoid the issues that we have with our hard simulator, that some parts were different and it caused issues. We had to change configuration. So the idea is to have a single package that can be used in any kind of system with the same configurations, right? Uh, Again, why exactly? Well, the QEMU has a high fidelity simulation, so it already has the Leon tree simulation on it also, and it can add components as needed. So we need to modify the QEMU kernel a bit, but we can add new components. We can create the exact same interface and the exact same address mapping and everything from the real instrument. Oh, sorry, from the real instrument to allow the virtualization to be as close as possible to what the software team is expecting. Right? And the Docker, because well, it's for deployments. The idea is to be able to quickly share and distribute it, and to run in servers or personal computers wherever they need to run. Another interesting part of the setup is the ability. Normally, you will have a few units of hardware, but if you have a virtualized instrument, you can run in any number of computers with any number of people working on parallel with them. Right? Okay, so this is just so the let's say the architecture that we arrived after thinking about it. So we have we call it Kemula. It's a modification of the Kemu. We have a container. This container shall have not only the Kemu machine emulating the virtualized processor, but also a system machine state controller, because to be a full simulator, we can't just emulate the system. We need to have all the control interface so they can stop the simulation, start it, and inject failures and get status and everything else. So it cannot be just a simulation of the instrument itself. You need not only to emulate the instrument, but also have all these other features. So everything is packaged and it's all the communications done by TCP/IP. So it was created to be as generic and flexible as possible, to be able to integrate in any environment. And you can connect it to an external code. This external code, it it control the machine, and it can send instructions. It can, for example, upload the new code. So if you have a code you want to test, you can upload this new code and let you run like it would be in the real hardware. And also it has this what you call instrument link and debug link. The instrument link simulates a real world instrument interface. So for example, the VenSpecM will use a spacewire interface. So this instrument link simulates this spacewire interface, and all data that goes through it is to uh, simulate and be equal to the real data trafficking on the space wire links of the spacecraft, of the instruments, right? And the debug link, it serves for debugging and control and seeing things that it's hard to see normally on the control link. It also has GDB support, so you can, for example, from a Eclipse interface, connect to the container and debug from there, line by line of code, everything you could do with your hardware. Okay. These are all features that Kemu natively already supports. So just to give an idea of what we are creating, right? Um, this is just another diagram showing the proposed software develop architecture. So you have the emulate environment with your system under test, and you have a data bridge that with external code that can act as a test simulator, a test analyzer, test monitor, so it can send specific comments, register then, see if it's responding to the telemetry correctly and everything that you need, actually, essentially. Since it all use TCP/IP connections, this external code can be, well, anything really. It can be Python, C++, it can be a red system. You have a lot of flexibility on the overall architecture. Okay. So again, the setup is we have the virtualized Leon tree or a similar CPU. I said similar because we are now working with the Leon tree, but the Kemu actually allows you to simulate a lot of different processors. So one thing that we are looking but not trying to implement right now is RISC-V emulation. So for newer emissions that are RISC-V based, we could also try to change the processor, right? Uh, it's very important to be able to inject the software binaries because you need to emulate the instruments from a software perspective. So every time they have the new software to test, they can inject it using standard interface, right? And the TCP/IP bridge allows you to run test script or even integration servers for automation. The internal state machine, it has two states, the config and run. In the config state, you don't have the virtualization running. So you can do all kind of configuration parameterization. For example, now I want my VinSpec M instrument to be using this data set for simulation or to work with these parameters. You can do all that on the config state. And when you go to a run state, your simulation actually starts. And then you have the equivalent of a real instrument running and waiting for you, right? Well, the possible architecture that we have the developed code, you inject in the QEMU environment. You have the emulated instrument communication with real protocols. So the biggest protocol for the SpecM is the SpaceWire one, but we also use a lot of WART to debug and interface. But theoretically, you could have bridge to any kind of internal protocol that you might need, right? And also you have the possibility of test script and fault injection, especially fault injection, because um, real space hardware cannot fail. So if you want to test a failure mode, it's very hard to do with real hardware. But with a virtualized instrument, you could very easily corrupt memory, you could very easily crash something, or any other thing you can consider that might happen, and test it as many times as you want without having worried about danification or causing issues to a real hardware, right? Right now, what we have integrated, as I commented, is SpaceWire. So we already have finished developing a SpaceWire link, but we already can send and transmit real equivalent real SpaceWire data. And we can also test this because we can use a stardom brick to communicate the TCP link with SpaceWire interface. So we can actually communicate the virtualized instrument with real instruments. Of course, this is all in slow speed for now. We still need to verify exactly how fast can we do this kind of thing, but it also enables the possibility of you easily integrating virtualized tools with real tools, right? And while WART is basic serial, it's very useful for base command, and it was the first interface that we started using to check the how would be the process of doing this kind of thing, right? And the photo injection, you can, as again, we can simulate stress tests and anomalies. For example, you can simulate that suddenly your VanSpec instrument is at 300 degrees and you need to deal with that, right? So you can corrupt memory, cause interruptions, cause timeouts. The list of auto injection is still being developed. That's why I don't have a formal list. But what I noticed on the hardware simulator that developed is that faults on the communication protocols is a huge issue, and faults on the simulation itself. So the image being corrupted or being not complete. So you are expecting 20 megabytes of data and you want to receive 19 megabytes. How you do this kind of thing without crashing your system? So it's the kind of thing that can very easily be simulated on this kind of instrument. So just, I know this picture is a bit, but just to have an idea of the internal state machine. So you have your user injecting the external code, everything's go by its PIP, and you have an internal machine that deals with all the commands. So you have commands to start simulation, stop simulation, pause, read memory content, inject memory content, and things like that. This is a process that this is a project that's still evolving. So at any time, our partners can chose to add something new or something that we are considering important that they didn't consider and things like that. Right? All of this integrate inside the container. So when you put on your computer or a server or anything else, you just run the Docker container and it has all the interfaces of everything you need to run without needing to install a lot of dependencies and to worry about the exact environment you're running. So the idea is not doing that right now, but our desire will be as we'll do a CI/CD pipeline that when you do a software commit, it's already builds and run the QEMU and check if everything appears to be okay or not. Right? You can do automated regression tests, cover metrics, fail logs. This is just possibilities that we envision. The project, we should by this year start creating the pipelines, the CI/CD pipelines, and for the injection. So by the end of the year, we'll probably have a good idea of what exactly can we do and don't do with this virtualization. Right? And the expected benefits is early detection of software issues, right? Especially without the hardware. And especially this is also interesting, the shared environment across global teams, right? So you don't have to share your machine. You can just share the virtual entity, and 3, 4 people can work on their own machines, on their own systems, and then integrate everything. Uh, since this is a very specific instrument, it's hard to envision this. But you have, if you had, for example, a more common feature, you could have uh, a lot of different people working on the same thing, right? So it makes sharing and compartmentalizing things easier. Again, the primary results we observed, the idea is that we can have faster development cycles and lower cost for initial testing and have multiple parallel test benches because you also can do parallel CI/CDs pipelines if you want to, and it makes collaboration easier. This was a problem for our hardware development because you need to deliver hardware and then deliver an image, and they need to burn software and burn FPGA images. The idea is now to deliver a simple package that they can run anytime they want, so on and condition. Also, important thing that we are doing to ensure that what we deliver actually makes sense is that we have a Geyser GR1712 board, and everything that we deliver, we first test on this board. So the behavior of the real world hardware has to be the same of the virtualized system for us to consider that it's okay, right? Uh, this helps us ensure that what we deliver is actually makes sense from a real world standpoint and it's not just an exercise. So we compare the real world and also we have tests. Again, this is just a setup we did with the GR712 board. We are here communicating a virtualized instrument with the real board using WART interface. So the real board process a few packets sent to the virtualized system that process the packets again, and they're communicating each other with real time. Of course, it's a very low load test, so we still need to verify exactly what would happen if you have a high load test or things like that. But shows the possibility, if you have the correct hardware, to even communicate real hardware with virtualized hardware under the right conditions. Right? The next step is do exactly this for the spacewire interface, and it's a lot faster and a lot more complicated, and see how things go. Okay. Just again, just the framework setup. This is that what we tested. So you have the physical counterpart and emulated QEMU environment. Both of them running the exactly same codes and communicating with external test entity that essentially made the data go from one to the other one. So they have the exact same code because then you can verify if they have the exact same behavior. Unfortunately, it have, which shows that QEMU has a high fidelity simulation. Well, the test was very good and allows us to see that apparently we're in the right way. But again, we need to test with high stress load that simulates more real conditions. The next steps that we plan, so this is something that we have been working for about 1.5 years, 2 years now. And the next steps to incorporate this year, incorporate the fault models and finish the spacewire on the hardware interface. Uh, we don't think it will be working on this mission, but one thing that we envision is the possibility to deploy in multi-instrument simulation. So theoretically, nothing stop you to have a virtualized spec M and a virtualize another instrument, both running and communicating with each other. Right? And do a hard real-time constraint analysis to see exactly how close to the timing simulation it is. Can it be used? Can it only be used for behavior functionality, or can it also be used to uh, check timing and similar things like that? So it's also something that's open that we need to check. Right? And the key takeaway is that virtualization adds agility to fight development. The idea is to use all these new tools and that you have, the pipeline integration, everything else with common software methodologies that are already used in the area. It should allow for early detection of errors, saving cost and time. Theoretically, you could also check if the specs will work on a real situation also. And well, the idea is to have a system that has potential synergy with other missions that are also Leon based or RISC-V based. We want to, after this mission is being helpful for us to actually build this thing and test it and validate it, but we want it to be open to other potential missions and utilizations. Okay. Just some acknowledged for our partners. So Instituto de Tecnologia, obviously, FAPESP and CNPq, CAPS, they're all granting agents from Brazil, and the German Aerospace Center for giving us this opportunity in the first place. Thank you very much for the attention.
Can I go? Oh, are we? Oh, so I think just one observation. I think the software in the loop framework, I think it's really checking out the functionalities or the behavior of the system. So we'd be really interested in finding out the real-time constraints analysis, right? I overheard the conversation about you guys talking about real time. It's really the timing gets you, right? So yeah, that would be my observation. Thank you.
Thank you very much for the observation. This is also something that we know we will need to get very detailed data to know the limits of what we're doing.
Hello, good talk. The last times I tried Chemo with Leon 3 had the limitation that you can use a single core. You still have that limitation? And another question is related with the last one. Is in Chemo you usually don't have cycling accuracy. Thus, you don't have timing accuracy that when you interface with a dynamic subsystem, maybe things don't behave right. I know that there exists KemuCAS, which is aimed to accomplish that. I don't know if you tried.
No, I didn't. We will take a better look at it actually, but we didn't try to have multiple cores yet, so I cannot answer your first question. I know that we can freely add new peripherals as you can see fit, and custom peripherals that mimic the mission configuration. For the timing, again, we know it doesn't emulate the hardware behavior that closely, so that's also something that we it's a big question. That is okay, developed, it works, it runs software, but for what kinds of validation can it really be used? Can it be used for all the validation, not just behavior validation, where it goes? And this is something that we want to explore this year, and if everything works, have a better answer by the end of the year. But yeah, we know this is a very important issue, and the one of the major difference between this being actually real useful tool or being just something that you use from time to time to check if it works.
Hey, thanks for the talk. You mentioned having automated tests written in CI. What sort of test framework did you use, if any, or is it hand-rolled?
For now, we haven't entered in the test part, but this is also something that we are developing together with our partners at DLR. So we'll probably try to use the tools they use and have their test bench running. For now, we internally are playing around with the GitHub Actions that's free and open source, and see what we need to actually run and what kind of comments we send and things like that. But it's still in development also. But
Do you have time?
Yeah, well, we can take one more right here.
Okay. What was the biggest challenge in making this simulator?
well, I'm more of a hardware oriented actually, so I was the responsible for creating the peripherals that could emulate the real hardware. And I believe one of the biggest challenge we had was exactly how to emulate such complex links, for example, space-wire interface, because we could just add a CPIB bridge and be okay with that, but we want to emulate as close as possible the protocol itself. So all the virtualization of the link behavior and interface and link on, the link state machine, how to send the data in the format that's compatible with SpaceWire, with end of package, and receive this data and be able to inject, for example, in the middle of a package, EEP, that's error end of package, simulates kind of failure. So how exactly to pick a real radar description of a complex system, complex communication protocol, and replicate this behavior as close as possible in virtualized software was the biggest challenge, I believe.
I thank you, Rodrigo.
Thank you all very much.